That's it, that looks fine now. Okay, so our next speaker is Veronika. She's going to tell us about the effect of metallicity on magnetic features in sun-like stars. And I'll give you a 3-minute warning before the end, Veronika. Off you go.
Thank you. Hello, everyone. And first, I would like to thank for the opportunity to present some of my results and some of the preliminary results that we have from 3D simulations. My name is Veronika and I work in the SOLVE group with Alexander Shapiro. And we are mainly interested in building onto solar knowledge and extend it to other sun-like stars and eventually to main sequence stars. So we are working on the connection between the sun and other stars. And I'm mostly interested in effects from magnetic fields and from metallicity. So we've heard a lot about surface magnetic fields, and I still would like to give a small introduction. So our sun, the surface of our sun is completely covered with magnetic fields, and these magnetic fields have different scales. So when we look at magnetic features, they are formed by large scale magnetic fields, and those we can characterize spots and faculae and network. However, if we look onto regions that we actually claim to be white regions of the sun, and we look closer, we see that they're actually also full of small scale magnetic fields. So on the right, you can see the plot, you can see a picture where the Hanley effect was used, and it was observed that even all the quiet regions in between have small scale magnetic fields. And these small scale magnetic fields, they can be, it was shown by Rempel and Vögler and Schüssler, that they can be explained by the local small scale dynamo that was introduced by Tanavir in his talk. And we have now 3D simulations that include the effect of a small scale dynamo operating on the surface of the convection zone. So yes, so let's further distinguish a little bit more on the magnetic fields. If we want to understand magnetic features, we have spots and faculae, and these phenomena are formed when magnetic flux tubes rise to the surface. So the magnetic tube will suppress convection motion underneath, and due to the magnetic pressure, it will also lower the density in the area where the magnetic flux tube is located. So in this nice scheme, you see that. So if we have here a magnetic flux tube, then we have a lower density in this region, and depending on the strength of the magnetic flux tube and the size, we either get faculae if it's small enough, because then the surroundings can heat this area and it becomes actually hotter and it becomes brighter. Or if we have large flux tubes, we form spots that are dark. However, so very good, so the magnetic features that we can observe on the sun, we have a very good knowledge of them. However, we cannot go to other stars. And we know that fundamental stellar parameters like the effective temperature and metallicity will have an effect on them. So as, for example, Mayuk presented his spot simulations, and this is also very exciting because we will soon have them also ready to run a radiative, more accurate radiative transfer on them to see how the contrasts look like. But for now, in this talk, I'll focus mainly on the small scale dynamo simulations and on some simulations where we have different activities for the faculae. So by activity, I mean that we introduce different mean magnetic flux of different mean strength, like Nadia in her talk, she had 100 Gauss, but you also have 200 Gauss, 300 Gauss, and 500 Gauss, and so on. Yeah, so but the main effect that I want to talk about is metallicity, and to do that, let's first step back and have a look on 1D investigations. So in order to understand if the metallicity actually really is important, we started our studies by using 1D models. And for the sun, there are several semi-empirical 1D models for faculae. And this is just an example plot from Vernazza, Everett, and Löser. And the C model is the average quiet sun. And if you go to network and faculae, the mean temperature, increases in the photosphere. So sorry. Yes. So if we want to go to different fundamental parameters, but we only have semi-empirical models, we have to make a couple of assumptions to extend these models. So the assumptions we made was that we assumed that the temperature difference that is applied to model magnetic features faculae remains the same. This is why our 1D model range for metallicity only covers a small range of metallicities, because if you just look at the self-consistently calculated atmospheric model for different metallicities, the effect is in the deeper layers, so somewhere here. So then we get the quiet regions, and then in order to get the faculae, we have to apply this temperature difference. So what can we learn from this extension? When we look at the faculae contrast, this is the left plot, in the Kepler filter for different metallicities, we see that, so this is the solar case, and so this is the faculae contrast. It's brighter in the center and gets even brighter further to the limb. If we then go to, say, higher metallicities, the contrast remains roughly the same, and then actually becomes darker towards the limb, but it's a brighter feature overall. And if we go to lower metallicities, what we saw is that the faculae contrast actually becomes dark in the center and then much brighter at the limb. So yes, so this is so if we then use this contrast and calculate light curves, for example, in the Kepler passband, then we can see this is here the solar case. Then we are mainly interested in brightness changes on the activity time scale, but also on the rotational time scale, as Timo was talking about. So on the activity time scale, for the solar case, if we go towards larger metallicities, we get a higher brightness change from the activity maximum to the activity minimum, because our faculae become much brighter. However, if we go to lower metallicities, we see actually a spot-dominated star all of a sudden, because our faculae become dark. Right, so we learn from the 1D models, because we are interested also in photometric brightness change and in these CLVs, that metallicity plays a significant role. And we also know that the 1D models are semi-empirical, and if we go to other stars, we only can cover a very small range, and we cannot capture 3D effects. So we need 3D models. So this is why we started to run 3D magneto-convection simulations for different metallicities. And this is also interesting for center-to-limb variation studies, because then we can calculate a very accurate CLVs, we can get photometric variability. But it's also interesting for ZDI, because the determination for now only takes into account effects of magnetic fields on the line. but we saw already even in the 1D models that there is an effect on the structure from stellar parameters and from magnetic fields. So let's go to 3D. So this is the rough grid that we want to cover for now. We have a different stellar types. This is what Tanavir showed, and I'm covering this axis with different metallicities. And for now, I'm focusing on the metallicity case -1, the solar metallicity, and the metallicity 0.5. This is just to illustrate how our cubes look like. We have Cartesian boxes of the upper convection zone and the photosphere. These are vertical magnetic fields. So in my study, I'm focusing on calculations with cubes of 9 × 9 megameters in the horizontal and 5 megameters deep. And they have roughly the same amount of pressure scale heights, because metallicity does not have such a huge effect as, for example, the effective temperature. I have simulations of the small scale dynamo taken into account, and also some runs with 300 Gauss mean magnetic flux to study different magnetic activity levels. But we also will have 100 and 200 and 500. There's one point I wanted to mention here. No, okay, let's go. Let's start with the results. So first, the effect of metallicity on the convection itself. This plot shows you the distribution of the vertical momentum in the layer around the optical surface, and the height of this layer is about 50 kilometers. So for the different metallicities, you can see that for the low metallicity case of -1, we have a much wider distribution of vertical momentum. It means that we have much more extreme values in the convection, much more momentum transport. If we then go to lower metallicities, to the solar case, and then to the 0.5 case, our distribution gets narrower and steeper. And this indicates, so this is the SSD run, and this indicates that that the convection becomes much more efficient for lower metallicity stars. And this is also a very good agreement with the stagger grid. The stagger grid is a grid of 3D calculations, but in pure hydrodynamics, without taking into account magnetic fields. Now, if you then have a look at the magnetic fields, so these are surface plots, 2D surface plots at the optical surface of the overall magnetic field strength. And when we go from the low metallicity case to the solar case, we see a difference in the structure, because we also see a slight difference in the convective structure, and we also have much more stronger fields in some cases. So we have higher magnetic field generation in the SSD run for low metallicity stars. And then if we go to higher metallicity stars, there's a subtle difference here, but you can also see that for the solar case, we still have some extremer magnetic field strength than for the higher metallicity star. So then if you look at the distribution of the magnetic fields in these 3 cases at the surface, time averaged, I mean that I'm taking many cubes over several hours, then you can see that the distribution for the low metallicity star peaks at higher magnetic strength than the two other cases, than the solar metallicity and the larger metallicity. And also the tail of the distribution shows that we have much less large magnetic field fields in the higher metallicity star. Yes, so what does it mean for the intensity now? Because this is something that we are also very much interested for observations. So if you look at the RMS intensity, and I've taken the same measure as the people in Stagger to have to be able to have a quantitative comparison as well, we see that the low metallicity star has a much higher RMS intensity, and there's just a little difference between the hydro case and the SSD case. And then if we go to solar metallicity and higher metallicity, we see that the difference between hydro and SSD becomes larger. So there is definitely definitely more, sorry, there are more contrasts in the hydro case than in the SSD case. And this also, so these 2 points I can compare with the Stagger, but this is just for hydro, and they also have a much higher RMS intensity for very low metallicity stars. But again, these are just only hydro simulations. Now, let's have a look at the overall distribution of the emergent intensity. So if we look at the same measure that Tanavir also showed us with the distribution of intensity, then we can definitely see that in both cases, here I unfortunately don't have the 0.5 run. We see that both metallicities, the solar and the -1, have bimodalities, but it is much more pronounced in the low metallicity star. And if we go from hydro to SSD, we have a small difference. And we have a much larger difference when we go to the case of a more active star with a mean magnetic flux of 300 Gauss. And we also see that our network is not as bright for the low metallicity case. Right, so here is just also one more plot that that shows the differences for the low metallicity stars going from hydro over SSD to 300 Gauss, and how our granulates become darker here for a much higher magnetic flux. Right, I think, yes, I think let me give you a summary of what we have so far and where we want to go. We understand from 1D models that metallicity has a significant effect on the structure in stars and on the contrasts. And we need to take this into account also when we calculate center to limb variations. From 3D calculations so far, we understand that lower metallicity stars have a much more vigorous convection at the upper layers, which will affect the magnetic field generation in the SSD run, but also will affect the magnetic field distribution for more active stars when we take into account 100, 200, 300 Gauss fields, vertical fields. And then, yes, so this also shows in the intensity distributions in these stars. And the study is not complete yet. So we are still running the simulations to get more metallicity cases, to get different activity levels, and we need to further post-process them and also run more accurate radiative transfer calculations with the MPS Atlas to get accurate spectra. And now I remember what I actually wanted to point out in this slide. So my calculations are in non-gray already, which is also important for the intensity distributions. Sorry about that. Yeah, thank you very much, and I'm happy to take questions.
Thank you very much, Veronika, for a really interesting talk. Questions for Veronika? I'm going to leap in while people are gathering their thoughts, Veronika. I was fascinated by your comment about faculae becoming dark for different metallicities. Is there a possibility to test this using occultations? So if you have a binary system where one star occults the other, could you test the location and the brightness of faculae?
I'm very sorry. This is not my expertise at all. I'm way much more into modeling. I would not, right from the top of my head, I would not be able to tell how you can test it in observations. Sorry. Maybe someone knows.
Maybe someone else who's listening will be able to set me right. I know that it's a great way to look at distributions of dark spots. In fact, I know Sandra did a very nice paper on this. And so I just wondered if you could use it for faculae as well. If you know the metallicity, could you have used occultations to test whether the faculae were dark? Anyway, it was just a random thought.
Can I jump in there?
Yes,
Sorry.
please.
Okay, Sasha, go ahead. I would have thought you can't tell if it is dark faculae or if it's a spot.
That's true. Yeah, that's probably true. Yeah.
Potentially central to limb variations might be very different. Yeah, and morphology of the light curves might be pretty different. Yeah, so like looking, for example, at the power spectrum of the light curves, there might be a chance. Yeah, whether we would really have it or not, of course, I have no idea. That's we need to put Veronika's simulations in it, look at power spectrum and look at light curves we would get, for example. Yeah, I'm talking about brightness variability, of course.
Okay, if there are no other questions, thank you very much.